So we're going to continue this lesson 1.3 that we started yesterday on transformations of function graphs, and what are the ways you can transform the graph of a function, y equals f of x. Yesterday we did it in much more general terms. We kind of explored it generically. Today we're actually going to use specific functions like x squared. We are still working on reasoning, so we're going to be seeing a lot of representations, and we're going to be thinking about numbers in a lot of different ways today. All right, so we're going to go all the way to where it says explain where we left off. There we go. Okay. So we're going to transform the graph of transforming the graph of the parent quadratic function. So there's actually two words just in that title. A quadratic function, remember, is an x squared function, and it makes that U-shaped curve. That's a parabola. You probably talked about that in Algebra 1. And then remember, a parent graph is the absolute most basic function that you can do in any function family. So like for lines, we would be talking about the line y equals x. For parabolas, we're talking about y equals x squared. So you can use transformations. Remember, a transformation is just something that moves a graph in the coordinate plane of the graph of a basic function called a parent function. So I'd probably underline basic function called parent function to obtain the graph of a related function. To do so, focus on how the transformations affect reference points on the graph of the parent function. So this book teaches it from not only using the vertex, but also using a couple of other points and then moving those points on the graph. So for instance, the parent quadratic function is f of x equals x squared. The graph of this function is a U-shaped curve called a parabola. Probably could underline that definition right there. With a turning point called a vertex. I'd underline turning point called a vertex. And in this case, the vertex is at 0, 0. Some other useful reference points are -1, 1, and 1, 1. So if we start every graph with those 3 points and we try to transform those 3 points on each graph. Okay, so we're going to describe how to transform the graph of f of x equals x squared to obtain the graph of the related function g of x. We're supposed to draw the graph of g of x. So they have actually stepped through all of this for us. We're going to go through and look at it, and then we'll try one together. They basically took this function that they gave us. So here's our function. Remember, we've got the a value, the b value is in front of the x, and it's an h and a k value. So the a value we learned yesterday it talks about being a vertical stretch. It's a vertical stretch with a factor of 3, and because of the negative in front, we have that reflection across the x-axis. In this case, the b value is 1, so it doesn't have a horizontal stretch or compression. Remember, when you come in or out of these parentheses with the x, that sign changes is opposite. So for our h, it's actually a +2. And that's the horizontal translation. When you're in or out of parentheses, it moves to the left or to the right. In this case, it was positive, so it goes to the right 2 units. And then outside the parentheses is our k value, or our y movement, which means it goes up and down. And in this case, the sign does stay the same. So it's a vertical translation of the graph down 4 units. So if we're going to actually apply these transformations to actual points, and we want to look at what's going on with the x value, the x value comes from both the b and the h. So there isn't a stretch or compression, so there's nothing we would multiply the x by. But because we have a horizontal translation, we would add 2 to the x. So they're saying that we're going to take that x coordinate and add 2 to it. Then the y value is affected by the a and the k. So the a would be a multiplied thing because it's a vertical stretch. So we would multiply the y by -3. And then to do the vertical translation down, we would subtract 4 from it. So that's where they're getting those little formulas from. So we're going to basically take our points and we're going to plug them into that transformation. So this first one is taking a -1 in for the x. So -1 plus 2 ends up being 1. And then we're going to plug a positive 1 in for the y value. So we've got negative 3 times 1 is negative 3 minus 4 is negative 7. So we're going to keep doing that. We're going to do that for the 0 and for the 1, 1. So we plug in a 0 to the x plus 2. We get 0 plus 2 is 2. And then we get negative 3 times, put the 0 in for the y, times 0 is 0, minus 4 is negative 4. We're going to plug in the 1, 1. So we put 1 plus 2 for the x plus 2, and that gives us a 3. And then negative 3 times 1 is negative 3 minus 4 is negative 7. And then all they did was they plotted the points and they made the U-shaped curve. Make sure you look, it's a U-shape, not a V-shape. All right, so let's try this together, okay? So we're going to try to fill in the chart that they've got there. Differences this time. Remember we've got the A value in front, the B value, the B value is actually the denominator there, and then we've got the H and the K. So it says, it kind of gives us a hint, since A equals 1, so we would write 1 there. There is no vertical stretch, no vertical compression, and no reflection because it was positive. The parent graph, so we have to talk about it being stretched or compressed. Because our B value is 2, okay, that would mean, so it's bigger than 1, so it's actually stretched horizontally by a factor of 2. There's no negative in front of it, so there's no reflection across the y-axis. The H value, remember we come in or out of parentheses, we switch the sign, so it's got to be negative 5. So the parent graph is translated negative 5, and in an x direction it would be horizontally. And then the K value is positive 2, because we keep the sign. The parent graph is translated 2 units, and K deals with y, so it's a vertical translation. So let's talk about their little formulas that they did for each one of the points. So again, the x coordinate is affected by the B and the H. So the B value is 2, and we multiply that by x, and then we subtract 5 from it. And then the y value is affected by A and K. So A is 1, so 1 times y is just the y, and then we're going to add the 2 for that vertical translation. All right, so we're applying those formulas to the 3 points of reference here. So we're going to put in a negative 1 into the x. 2 times negative 1 is negative 2, minus 5 is negative 7. And then we put the 1 in for the y. 1 plus 2 is 3. We're going to put in the zeros now. So 2 times 0 is 0, minus 5 is negative 5. And then 0 plus 2 is 2. We're going to put in the 1, or the 1, 1 point. So we get 2 times 1 is 2, minus 5 is negative 3. And then we plug in the 1 for the y. So 1 plus 2 is 3. We're going to go ahead and plot those 3 points. So we've got negative 7, positive 3, negative 5, positive 2, and negative 3, positive 3. And go ahead and connect the dots with a U-shaped curve. All right, so now we're going to go ahead and reflect on this a little bit. So it's asking us, is the function of f of x equals x squared an even function, an odd function, or neither? So remember the definition that we talked about yesterday. It told us that we had to plug in a negative x. So if I did that really quick, so if I do f of negative x equals negative x squared, well, if I calculate that, the negative goes away with the squared, so I'd get back to x squared. So I got back to the original, which means it's an even function. So let's see if we can form that into a little bit of a sentence. So we would say that f of x equals x squared is even because f of x f of negative x ends up equaling the original function f of x. And probably to make that a little bit more precise, we would say for all values of x in its domain. All right. Then it's asking us in 11, the graph of the parent quadratic function f of x equals x squared has the vertical line x equals 0 as its axis of symmetry. So let's go look at that. Let's look at that picture. So there's our x squared. If I were to draw that axis of symmetry, so remember an axis of symmetry, if I fold on it, it's the same on both sides. Notice it goes through the vertex point, and the equation of that line would be x equals 0, which happens to be the x value on that coordinate there. So let's read the rest of the question now. Identify the axis of symmetry for the graphs of g of x in parts A and B. Which transformations affect the location of the axis of symmetry? All right, so let's look at graph A. If I look at this axis of symmetry, it looks like it would be at x equals 2. And then in this graph here, if I look at this axis of symmetry, it looks like it would be at x equals -5. And again, those are all coming for those happen to match those h values. So it's that horizontal translation that's affecting those changes. So we would want to say part A axis of symmetry, I'm abbreviating AOS, is x equals 2. And part B axis of symmetry is x equals -5. And you could say a horizontal translation affects the location of the axis of symmetry. It's the location of the axis of symmetry. All right, so we're going to go ahead and we're going to try this on our own together here. So we're in those, they didn't give us any skeletons, so we have to kind of figure it out on our own here. Describe how the transformation of the graph of f of x equals x squared to obtain the graph of the related function g of x equals f of -4 of x minus 3 plus 1. So remember the a value is always in front, the b value is in front of the x, the h is inside the parentheses with the x, and the k is on the outside of the parentheses. So the a value is equal to 1. So there really isn't, so that means that there is no vertical stretch or compression. The b value is interesting this time. You'll notice that in this one back here, oops, sorry, too close to the top. This one right here, the b value is really coming from that denominator. So it was a fraction 1/2. You notice in this one, it's an integer -4. So it actually means that the b value ends up being, it flips the reciprocal. It's a 1/4. So b equals 1/4. And then we also know that it is, so it's a horizontal compression because it's between 0 and 1. And we also know that it's a reflection because of that negative, right? And a reflection, and in this case, because it's the b, it would be across the y-axis. Reflection across the y-axis. Excuse me. And then the h value is, we switch our signs, so the h value is 3. And then the k value, so that would be a, horizontal translation to the right 3. And then the k value has to be 1, which is a vertical translation. And then it's positive, so it's going up 1. All right, so let's see if we can get a little generic formula for our x and our y coordinates. So again, the x is affected by the b and the h. So I would have to, and actually I should have probably put a negative in front of that 1/4. So I'd have to multiply the x by negative 1/4 and then add 3 to it. And then the y is affected by the a and the k. So the a is 1, that doesn't do anything to the front of the y, and then plus 1. So now we're going to put this into the 3 points, negative 1, 1, 0, 0, and 1, 1. All right, so let's see, negative 1. So negative 1/4 times negative 1 plus 3. So negative 1/4 times negative 1 is 1/4 plus 3 would be 3 and 1/4. And then we're going to put the 1 into the y plus 1. So 1 plus 1 is 2. Then we have negative 1/4 times 0 plus 3. Negative 1/4 times 0 is 0, plus 3 is 3. And we substitute the 0 in for the y. So 0 plus 1 is 1. And then we've got negative 1/4 times 1 plus 3. Negative 1/4 times 1 is negative 1/4 plus 3. So 3 minus 1/4 would be 2 and 3/4. And then we plug a 1 into the y. 1 plus 1 is 2. Let's go ahead and plot those because that's the last little bit that we have to do. So we've got to go out 3 1/4 and up 2. And go out 3, 1. We're going to go out 2 3/4. So this thing is a super, super skinny graph. All right, we have one more explain that we've got to do, and then that is it for this lesson. So we're modeling with a quadratic function. So you can model real-world objects that have a parabolic shape using a quadratic function. In order to fit the function's graph to the shape of the object, you will need to determine the values of the parameters of the function. G of x equals a times f of 1 over b times x minus h plus k, where f of x equals x squared. Note that because f of x is simply squaring a function, it's possible to pull the parameter b outside of the function, combine it with the a parameter. So basically they're saying I can take this and it gets combined with that a outside, so it really makes this new function that we're looking at, g of x equals a times f of x minus h plus k. So it's down to 3 parameters instead of the 4. When modeling real-world objects, remember to restrict the domain of this function to the values of x that are based on the object's dimensions. So if I kind of looked at this first one, looked ahead, I would just stick to these endpoints that they give us here. So in example 2, we have an old stone bridge over a river uses a parabolic arch for support. In the illustration shown, the unit of measurement for both axes is feet, and the vertex of the arch is point C. We're going to find a quadratic function that models the arch and state the domain of the function. So we've got to find a function that models that arch for us. So we're going to start by, and so they're showing us really how to model this problem. We're going to analyze the information that we have. So the shape of an arch is a, and they told us that in the paragraph there, it's a parabola. And the vertex of the parabola was point C, which was 27, negative 5. And the other 2 points on the parabola, I could go back and look at those and read them off of there, but we could go ahead and we're going to write down those 2 points. So is 2, negative 20, and 52, negative 20. So we're now going to formulate a plan. So you want to find the values of the parameters a, h, and k in the g of x function, where f of x equals x squared. You can use the coordinates for point C to find the values of h and k. Then you can use the coordinates for one of the other points to find the value of a. So basically, we're going to plug in the points for the value, or the h and the k values from C, and then we can pick one of the other 2 points to help us solve for a. So now we're going to actually solve it. So the vertex of the graph of G is point C, and the vertex of the graph of f of x is the origin. Point C is the result of translating the origin 27 units to the right and 5 units down. This means that h equals 27 and k equals -5. We're going to substitute these values into g of x, and it gives us this function right here. Okay. Now substitute the coordinates of point B into g of x and solve for a. It doesn't matter if you use point A or point B. Okay. So it says we're going to write the general function, which they did for us. We're now going to substitute 52 in for x. So they substituted it in here, and we're going to put it in here for that x. Now, we know that g of 52, it's just another way. So we had that point. Sorry, what was it? I lost it. 52 -20. So 52 -20 was the point. Another fancy way to write that is, in this case, g of 52 equals -20. See how it's the same thing? It's just written here as a function, and then here is a coordinate point. So it means the same thing. So we know that g of 52 can be replaced with -20. So that's what they did here. And then the value, the y value of b. So now we're going to do some arithmetic. So 52 minus 27 is 25. So now I need to find f of 25, and this is what's really kind of stinky about this. You have to know your f function, and we know our f function is back here, is x squared. So we're going to apply that x squared to this. So that really means we're taking 25 and we're squaring it, which is 625. Then we've got to solve for a, so I would probably start by adding the 5, which is, is that what they did? Yep, add the 5, so you get, no it's not. It's gotta be. Add the 5, so you get -15 equals 625a, and then you go divide by the 625, so you get -15 over 625, which if I look at that, 5 goes into both of them, so I can reduce that to -3 over 125. And then what you do is you plug it back into that generic function. So we put the a back in for we put the -3 over 125 back in for the a, and we use our h and our k values from before. Now we were supposed to talk about the domain, right? And again, I don't care which type of notation you use. They use the set notation there. So all I have to do for the domain, remember it's x values. So I'm going to go back here. I'm going to leave the beginning and the end x value and put those on either end of the domain. All right, they have us looking at justifying our answer. Again, this is something that's up to you on a test. It's good to do, but if you ran out of time, it's not 100% necessary. So we're going to write the function, and then you're going to substitute in it. Well, so basically, we're going to take that up. So we're going to use our other point that they gave us to try to check this. So we're going to plug in the 2 for the x, so both places where there was an x. And this is just notation. It says when we evaluate g of 2, what we're going to get is what's on the right side here. So 2 minus 27 is -25. Again, we need to apply the f function, okay? So we know that f of -25, remember f is x squared, so really -25 squared would be 625. And then 625, let's see, I could simplify here, couldn't I? 125, you know 5 goes into both of those, or 25 goes into both of those. 25 goes in there 5 times. And in there. goes in there 25 times. And then we know 5 goes into 25 5 times. So really I have negative 3 times 5, which is negative 15, minus 5 is in fact the negative 20, which is the value that we were looking for. So it did actually, what we did, our equation actually worked with the other point. All right, we're going to do one more here, and then that's it. So the netting of an empty hammock hangs between its supports along a curve that can be modeled by a parabola. In the illustration shown, the unit of the measurement for both axes is feet, and the vertex of the curve is point C. Find a quadratic function that models the hammock's netting and state the function's domain. We could do the domain right now, couldn't we? Couldn't we take this value and write our little inequality? So we would say the domain is of g of x is, and we could use, if you want to use little set notation, we can. So x bar, and we have it's between negative 2 less than or equal to x less than or equal to 8. So we've got that piece of the question answered. We still need to find the quadratic function. So let's start with our generic function. So g of x equals a times f of x minus h plus k. All right, let's see if we can figure out what all of those parts are. Oops, sorry. So we know that the h and k come from there, and it looks like I've got a positive 3, so that flips into x minus 3. And then, because in or out of parentheses, we switch the sign, and then we're going to add the other 3 to the end. We don't know the a value. So now we're going to go ahead and pick one of the points. It doesn't matter which one. I'm going to choose negative 2, 4. So we're going to put in negative 2 in for the x. So g of negative 2 equals a times f of negative 2 minus 3 plus 3. So if I did some simplification there, I'm really looking for f of negative 5 plus 3. So remember, your f function is x squared. So I need to apply the of x squared function to the negative 5. So negative 5 squared is 25. So we get g of negative 2. Ooh, we know what g of negative 2 is, don't we? Let me fix that. Maybe not. Sorry. Where did it go? Okay, there it is. I'm going to go here and erase that. Okay. Go back to here. All right, so we know that g of negative 2 is actually that 4 value, so I can substitute that in. For the f of negative 5, we calculated that to be 25 plus, that's a plus 3. So I'm going to go ahead and move the 3 over. So 4 minus the 3 would be 1 equals 25a. So a ends up being 1 over 25. So I'm going to go ahead and put that back kind of into the formula right there. So g of x equals 1 over 25 f of x minus 3 plus 3. And if we were taking a test, we would take this other 0.84 and plug it in, and just to make sure that we actually had that right. So to finish getting your class points for the day, you need to fill out the elaborate section. So you're going to do 14, 15, and 16 today.